Hello, this is our continuation of our discussion on the chemistry of life. We're going to continue with our PowerPoint looking at the chemistry of life. So I'm going to switch to full screen load here and move forward. So looking at matter and energy. Matter is the stuff we are made of. We are made of solid, liquids, and gas. If you look at the arrangement of atoms in a solid, we can see that they are in fixed positions with strong bonds. It takes more energy to break apart the particles in a solid than it does a liquid. Liquids have weak bonds holding them together, so they are loosely held. They take the shape of their container. They flow past one another. Examples of liquids in the body would be our blood and urine and the water that is found inside and outside of our cells. Gases are not bound to each other. They're free-floating, free-moving particles that bounce off the walls of their container, and that's what exerts pressure. When we talk about gas pressure, we're talking about the pressure of those particles against the walls of the container, or the force that they exert on the walls of the container. So the higher the pressure, the more energy those gas particles have. Plasma is a special type of matter. It's a mixture between a liquid and a gas in terms of properties, and that's what the sun is made out of. So we're not going to go into detail on plasma in terms of as a state of matter because it doesn't involve the human body. When we take these particles and apply heat to them, for example, we're giving energy to those particles. So when we put matter in motion, we call that energy. And one type of energy is mechanical energy. There's other forms of energy, especially when it comes to what we use in the body, and one of those is chemical energy. Chemical energy is the energy that we see stored in bonds between atoms in a compound or a molecule. For example, the sugar that we find in fruit has energy stored in the bonds of those sugar molecules. When we take that into our bodies and digest that, we release the energy from those chemical bonds, and we can use that energy to make new molecules. So that's an example of chemical energy. The same is true in gasoline. This can of gasoline has gas in it, and when we pour that gasoline into our cars and we burn that in our engines, we convert the energy and the chemical bonds of that gas into a usable form of energy for the car, which makes the engine parts move. So we're converting chemical energy to mechanical energy. This diagram here of the turbines, the top of the turbines that goes around and around when the wind blows at it, that's an example of mechanical energy. It's moving parts. Using your pencil while you write on a piece of paper, that also is an example of mechanical energy. Radiant energy is energy from the sun, energy that shines down in the form of electromagnetic rays. That's an example of radiant energy. So plants use radiant energy to make chemical energy. They make glucose from the sun shining on their leaves with the help of the process of photosynthesis. So that's radiant energy. The example shown in this picture is what we call electrical energy. It's due to the movement of electrons from a negative pole to a positive pole through an electronic device. So coming from the negative side of the battery to the positive side, that is electrical energy. Okay, now we're going to talk about the structure of atoms, and this is primarily found in Chapter 2 of your textbook. Just basic review of atomic structure. If we look at any atom that we see in the periodic table, it's composed of protons and neutrons, which are found only in the nucleus, and they stay in the nucleus. Protons have a mass of 1 and a charge of positive 1, or have a positive charge, and neutrons are neutral. They do not have a charge, but they also have a mass of 1. So we know that the atomic mass of any atom is based on the number of protons plus the number of neutrons in the nucleus of that atom. So we have a positively charged protons in the nucleus, and then outside the nucleus in these energy levels are electrons. Electrons are negatively charged. They have a very negligible mass, which means we don't really count their mass because their mass is so very, very small. So we can essentially say they have a mass of 0 because it's very, very close to 0. Whereas the protons and neutrons each have a mass of 1. And when we use units for the masses of these very tiny particles, we use AMU, which is atomic mass units. So neutrons have a mass of 1 AMU, protons have a mass of 1 AMU, and electrons have a mass of 0 AMU. And again, electrons are negatively charged, found in these energy levels outside the nucleus. The first energy level closest to the nucleus can hold a maximum of 2 electrons, and then every energy level outside of the first energy level can hold a maximum of 8 electrons. So when we find out what the atomic number of an atom is, let's say it's atomic number 11, we can figure out what energy level those electrons are by filling them from the first energy level and working our way out. So there'd be 2 in the first energy level, 8 in the next energy level, and 1 in the third energy level to make a total of 11 electrons. And we'll go over that again in the next couple slides. So the atomic number is what we see in the periodic table. It's the top number above the symbol in the periodic table. So if we look at this example, sodium has an atomic number of 11. It's at element number 11 in the periodic table. If you look in your textbook, there is a periodic table on page 582 that you can see sodium is in the first column of the periodic table, and it has the number 11 written above it. So that tells us that there are 11 protons and 11 electrons in an atom of sodium. The mass number is the number below the element symbol, so the number we see below Na in the periodic table for sodium is 22.990. Well, if we round that to a whole number, that's 23. We call that the mass number. The mass number is based on how many protons and neutrons there are in the nucleus, because the nucleus is where the mass of that atom is found, because the electrons, we already said, has a very negligible mass, so therefore the protons and the neutrons are what makes up the mass of the atom. So we can see in this case, we know there's 11 protons, and we know that the mass of one proton and the mass of one neutron are both 1, so therefore I can find the number of neutrons by taking the mass number and subtracting the atomic number. So I know there's 23 for the mass number, and there's 11 for the atomic number, so I can end up with 12 as the number of neutrons, taking the mass number minus the atomic number, because we know from the atomic number that there's 11 protons and 11 electrons, and we know the mass number is 23, so therefore the number of neutrons can just be found by subtracting the mass number minus the atomic number to get the number of neutrons, which would in this case for sodium would be 12. So looking at this chart here, we can see the chemical symbols here, the number of protons, number of neutrons, and electrons. We can figure that out by figuring out what the atomic mass is. So for hydrogen, it has an atomic number of 1, so that means there's 1 proton, 1 electron, and the mass number is also 1, so therefore there must be no neutrons, because if there was a neutron, then the mass number would be 2, because we know in the nucleus there's protons and neutrons added together to make the mass number. So if we look at nitrogen, we can predict what would the mass number be. If there's 7 protons and 7 neutrons, the mass number for nitrogen must be 14. And if we look in the 5th purple row on your periodic chart on page 582, we can see, or the 5th column, we can see that nitrogen does have a mass number of 14. So we add up the protons and neutrons to find the mass number. And remember, the protons and the electrons is the atomic number, and those numbers are the same because every atom is neutral. There's an equal number of protons as there is electrons. In looking at the periodic table here, we can see there's atoms that are arranged according to the number of protons and electrons they have, and particularly the number of electrons in the outer energy level is what arranges them in groups. So in group 1 of the periodic table, they have 1 electron in the outer energy level. Group 2, they have 2 electrons in the outer energy level. And if I move over here, this is group 3, there's 3 outer energy electrons. And then we get to the other side of this colored staircase here, the rules change a little bit, and we'll talk about that because these are non-metals on the right hand side, and we'll talk about how they're involved in bonding in a little bit. So isotopes. Isotopes are atoms that have a different number of neutrons than what we would normally see in a stable atom in nature. So we use these special atoms that have different numbers of neutrons because they give off radiation in the process of going from an unstable atom with more neutrons to a stable atom with less neutrons. For example, if we look at iodine, its atomic number 53, it has an atomic mass of 127. In this atom of iodine, it has an atomic mass of 131. Where do the extra masses come from? That's from the extra neutrons in the nucleus. So this would have 4 more extra neutrons compared to iodine that we see in the periodic chart that has an atomic number of 127, because 131 minus 127 is 4. So there's 4 extra neutrons in this atom of iodine. And those 4 extra neutrons will emit particles as it becomes more stable, and we use those particles in the form of, because they give off that's a type of radiation as those particles are released from the nucleus, and we use that to destroy thyroid tissue. We can also use it to absorb into tissues and for diagnostic testing, for PET scans. So radioactive isotopes are useful in medicine for not only treating disease but also diagnosing diseases. And that's where we see radium and cobalt-60. Those are 2 other isotopes that we use in medicine. Carbon-14 is found in all living things, and it slowly decays back down to carbon-12, which is the stable atom of carbon, and we use that for radioactive dating. If you find a fossil out in archaeological dig out in Egypt, we can compare the number of carbon-14 atoms to the number of carbon-12 atoms in that specimen to determine how old it is. Obviously, the more carbon-14 it has, the younger the specimen. Chemical bonds. There's 2 types of chemical bonds that are important in the body, as well as a third type that we're not going to talk about until you get to general A&P. But the first 2 we're going to talk about and focus on are ionic and covalent bonds. Ionic bonds are formed between 2 atoms that have outer energy levels that are not full of electrons. So we look at an atom, and if the outer energy level does not have 8, or if it's the first energy level, if it does not have 2 electrons in that outer energy level, then we say that it is able to bond with other atoms. So we'll look at that in more detail first. First of all, let's talk about the covalent bonds. Covalent bonds are formed between 2 atoms that overlap their outer energy levels, so they share outer energy electrons, and it feels to that atom like that outer energy level is complete. I have a YouTube video here that we can watch to show. I have to go out of PowerPoint for a minute to show that process. So here we can see these
interact or bond with
hydrogen
one another so as to
atoms have 1 outer energy electron, because according to its atomic number it has 1 electron, 1 proton, so there's 1 electron in the outer energy level. Remember, we said that first outer energy level is filled when it has 2 electrons. So hydrogen needs 1 more electron in the outer energy level to be considered stable and full. So it is looking for another electron. If it comes near another hydrogen atom, then it will share the outer energy level electron of the other hydrogen atom, so it feels like each atom has 2. And this animation shows how that occurs. So here's 2 hydrogen atoms, and by overlapping outer energy levels, those electrons spend a little bit of time around one atom and a little bit of time around the other atom, in the sense that it feels like there's 2. Here we can see oxygen. Oxygen also will share outer energy electrons. Methane, this is a carbon atom with 4 hydrogen atoms around it, forming covalent bonds. Going back, we can see water. I'll go forward here, if I can pause it. So we have water here. This is an oxygen with 2 hydrogen atoms, again sharing outer energy level electrons. So when we share outer energy electrons, again, we are forming covalent bonds. The other type of bond is an ionic bond. And an ionic bond is when one atom loses an electron and the other atom gains an electron. We see this occurring between metals and nonmetals in the periodic table. So if you look at atoms in groups 1, 2, and 3A, those primarily, and part of 4A, primarily form ionic bonds with atoms in groups 5, 6, and 7A because they have unfilled outer energy levels and they will lose an electron to become filled. So we have an example here shown in this animation. So this is an example. Sodium and chlorine. If we look at the atomic number of sodium and chlorine, 11 and 17, if we fill those electrons, we'll see there's a maximum of 2 that go in the first energy level, 8 in the next energy level. So we have 2 plus 8 is 10. The next electron would, to get to number 11, would have to go in the third energy level. So we have 2, 8, and 1. So that outer energy level is not filled with 8. Because remember, the first energy level can be filled with 2. Everyone after that must have 8. So there's only one outer energy level in that, one electron in that outer energy level for sodium. If we look at chlorine, chlorine has 2 electrons in the first energy level, 8 in the next, and to get to 17 total electrons, there must be 7 in the outer energy level. So if we compare these outer energy levels, neither are full, but by forming an ionic bond, sodium and chlorine can both have full outer energy levels. The first outer energy, or the one electron in the outer energy level of sodium will leave the sodium atom and become part of the outer energy level of the chlorine atom. By losing this outer energy electron, the next lower energy level becomes the outer energy level, and that's full with 8. So then sodium is considered stable. Chlorine, when it gains that outer energy level from sodium, it now has 8 in its outer energy level, and it is considered more stable. So when sodium and chlorine come in contact with each other out in nature, they form an ionic bond, and sodium chloride is what we know as salt, table salt. And it's also an important electrolyte in our blood. So sodium by itself, when it has this one outer energy electron, we call that elemental sodium, and that is a silvery white metal that's highly reactive with water. If we see chlorine, elemental chlorine, with just the 7 outer energy electrons, that is a green poisonous gas. However, when they form an ionic bond, and this electron leaves sodium and goes to chlorine, and they form the bond, then we have table salt. So the chemical properties change when we exchange electrons or we move electrons from one atom to another. They become totally different substances with totally different properties, like table salt. So what we call an atom that has gained an electron, we call it an anion. It's negatively charged because it gained an electron from another atom. So in the case of chlorine, chlorine has 17 protons, 17 electrons. But if it gains an electron from sodium, then it has 18 electrons, still has the 17 protons, so it has a net negative 1 charge because it has an extra electron compared to the number of protons. The cation is an atom in an ionic bond that is positively charged because it lost an electron. In the case of sodium, sodium lost 1 electron to chlorine. Sodium has 11 protons and 11 electrons normally, but if it lost 1 electron to chlorine, then it has 10 electrons and 11 protons, so it has a net positive charge, and that is sodium ion, we call it. Sodium ion would be written Na+, and chloride ion would be written Cl-. So when we take these ions in solution, which is what you see when someone has an IV bag because of dehydration or maybe some other health condition causing them to lose electrolytes, we need to replace those electrolytes via these IV fluids. So when we take salt into our body, those ions in that ionic compound of sodium chloride will separate from one another, and they're surrounded by water molecules. And the negative side of the water molecule, the water molecules have a slightly negative side and a slightly positive side. The oxygen portion of the water molecule is slightly negative. The hydrogen side of the water molecule is slightly positive. So those parts will surround each ion because opposite charges attract, and it separates those ions from each other in solution. So that sodium ion can actually leave the solution, cross the plasma membrane, and participate in nerve or muscle cell activity. And we'll learn about that when we get into those systems. But for now, just know that electrolytes are called electrolytes because they are charged particles that can actually conduct electricity. So that's why they're called electrolytes. But they're simply ions dissolved in solution that have either gained or lost electrons. We'll pick up with pH in our next lecture discussion.